Arnaud, are you on the line? Arnaud?
Can you hear me?
Yep, I can hear you now. And we're ready to go whenever you are.
All right. Okay. So I'm Arnaud Venet, and I work in the robot software engineering group at NASA Ames Research Center. And in this talk, I would like to discuss our experience in designing static analysis tools to help formally verify Microsoft software. This work is funded by the SSAT project, Aviation Safety Program, under the Aeronautics Research National Program.
Your slides disappeared there for a second, Arnaud. I'm loading them again right now.
Okay, I get it. Yeah, right. So, a quick overview of the talk. So, we first describe what it means to this physical system and why soundness is important to.
Arnaud?
Oh, yeah.
Are you close to your telephone? Because we're having difficulty with your connection. If you could get close to the microphone on your telephone, we might be able to hear you better.
Okay. I'm just holding the handset. I'm not sure I can get any closer.
Oh, that's better right there.
Is it better?
Yes, thank you.
Okay. Okay. So, well, okay. So we'll see what it means to do static analysis for physical systems and why it's difficult to design static analyzers that are sound, which is an important requirement for doing verification. And we describe our approach to address the engineering of sound static analyzers using a platform that we are currently developing, and that's called IKOS. And we will conclude by describing a few applications of IKOS. First, let's go over static analysis. So you must all be familiar with static analysis technology. Typically, a static analyzer takes source code and produces a number of elements of information. So it could be a list of bugs or defects, like most bug finders do. It could be some proofs, some actual certificates of correctness, showing, for example, the absence of one-time error, addition by zero, or arithmetic overflows. Or it could be information about the code itself, at the range of variables or certain programming variants. And static analysis is important because it brings a new level of software assurance that testing can't meet. For example, there was an incident that occurred on the flight of an Airbus A330, where all cockpit displays shut down for about 40 seconds. And it appeared that that error was due to a counter in the software that was completely displayed that was regularly incremented and that was never reset. And that counter caused an arithmetic overflow after exactly 96 hours of operation. And it's something that's extremely difficult to find just by testing. And in fact, the error was corrected by adding an item in the pilot checklist, which is to reboot the computer before each takeoff. And there are other types of errors, like buffer overflow, addressing in a way outside of its bounds, that may just be extremely difficult to detect by testing because the consequence can be the corruption of memory, a part of memory, and the effects could be felt much later during flight during organization. And in order to use static analysis to address these issues, it's important to have a small property that's called soundness. Soundness means that the tool doesn't produce any false negatives. It means that no potential error on the total chart, of course, is ever missed by the tool. And you have plenty of commercial tools that are not sound, like Causality Prevent, Clockwork, etc. And they may miss errors. And you have a few tools like Polyspace or S3 that bring a very high level of assurance because they are sound. That's what we are interested in. And whereas sound tools that are not sound are relatively easy to use and apply, it's a little more difficult for sound stabilizers because in order to be effective and get a low rate of false positives, the analysis algorithms must be specialized, and you need a lot of parameterization in order to tailor the tool to a certain application. And that's the main challenge of applying sound static analysis. Because if a tool is too specialized, like the S3 verifier that's used by Airbus, and you get a very low rate of false alarms, almost zero in the case of S3, but you can only apply the tool to a very restricted subset of application. In that case, essentially, code inherited from the CADE development suite. But if you use general purpose tools like Polyspace verifiers that can handle a larger set of applications, then you can run into scalability issues, and also you can get a lot more false alarms that entail a lot of manual review. So, one thing that we need is the ability to customize a stabilizer for an application. And we tried that in the robot software engineering group at AIM. And we developed a Scalable surveyor a few years ago in order to analyze a certain family of flight software used in the Mars exploration program. Missions like Mars Pathfinder or Mars exploration rovers. And the code used in the mission is quite complex, but follows a very similar architecture. So we developed that tool, and we obtained very good results. We were able to analyze the whole flight system of Mars exploration rover, which was over 500,000 lines of code, and with a low false alarm rate. But the problem is it was a time-consuming effort. It required a lot of expertise to build such a analysis tool. And if we want to modify modify the characteristics of the tool, the properties analyzed, or if you want to increase the precision, we might have to do really significant changes that would sometimes entail almost rewriting the whole tool. So it's interesting, but it's not very practical. So we started investigating how we could generalize this approach. So is it possible to really streamline the development of a specialized static analyzer? And what we need is to have an open architecture so that we can have a fine-grained access to the algorithm, and we can combine them in a way that's precise and scalable for certain type of application. But we don't want to rewrite all the algorithms, all those algorithms. So they have to be encapsulated in some high-level API. And that's why we came up with this new design for IKOS. And IKOS stands for Inference Kernel for Open Static Analyzer. And it's essentially a library of static analysis blocks that's written in C++. And all these blocks encapsulate all the basic functionalities of a static analyzer. And we can combine those algorithmic blocks to effectively build a real static analyzer for real C and C++ programs. And in fact, we have done exactly that for a buffer overflow analyzer. And it takes less than 7 lines of C++ just to build an interprocedural buffer overflow analyzer for real C programs. And that's because we believe that a major step toward using sound analysis and building customized analyzers in a more effective way. And in order to use this static analysis effectively, we also need a front end that's flexible and practical. Because there is one untold story or nasty little secret of static analysis is that just getting the source code to pass to be accepted by the tool is extremely difficult. And most commercial tools have a front end that's very fuzzy and usually accept standard C or C++ code. And the problem that's the source code that you analyze, especially when you deal with this embedded software, like typical software, is rarely standard. You have some Alex of C that could be used, and that may require a lot of changes in the source code just in order to have it to get it analyzed. And in order to solve this issue, IKOS stands on a front end called LLVM, that stands for Low-Level Virtual Machine. And this front end does not have anything in particular that sets it apart aside from the other C front end. But for the fact that the GCC compiler can produce LLVM code. And that's really a major differentiator. Because we had an example of the autopilot for UAV that we wanted to that we management could be used instead of expression, and all the commercial tools we were using failed to pass the code because of that, except IKOS, because we had GCC that could support this extension without any difficulty. But something that's quite important. It's a very important aspect to consider. So this is the big picture for IKOS. We use, as I mentioned, GCC to compile the application and get an LLVM representation. So it's just a special type of executable. And on the right-hand side, we have IKOS that's made of a number of C++ classes that each encapsulate a certain type of algorithm for sound state analysis. And we can assemble those objects in order to build an analyzer that gets the LLVM code and find some properties. And then a verifier that interprets those properties in order to verify a number of checks of predetermined technical conditions, like the absence of buffer overflows, and yield a verification report. For example, if you consider this small piece of code, the analysis part would infer two types of properties. For example, using the domain of intervals, you would find out that the second argument of the function f is always between 0 and 7. And using pointer analysis, that's part of the IKOS library, we would find out that the pointer p, the first argument of f, points to the fourth element of the structure f. And using these two properties, a buffer overflow verifier would check that the pointer access within the loop always occurs within the bounds of an allocated object. And so we can check lower bound compliance. And this is true whenever the structure S has at least 11 elements. So most applications work, most generators deal with IKOS work in that way, using an analysis part and then a verification part. And all the specialization really amounts to finding the right blend of algorithms, the right combination of IKOS building blocks in order to produce properties that are strong enough for verification, that would yield a low rate of false alarms, and that are efficient enough to compute. So we want to be both precise and scalable. And this process is essentially empirical. There is no universal rule or guidelines to follow. It really depends on each application. And having state analyzers that can be built rapidly and concisely with IKOS allows us really to experiment with different combinations and find a good trade-off between scalability and precision. So we really have a way of streamlining the design of those guidelines. So now let's go over a few applications of IKOS on the real code. One of the first applications was the analysis of unmanned aircraft autopilots, UAVs or UAS, as they are called now. It's a very important problem in aeronautics, especially in the context of the next gen, because UAVs are slated to operate in the NAS, and there is a need to certify the flight software. And fortunately, there's a large variety of codes, platforms used in UAVs, and don't have any real standard and development and certification process, like U-178 that is used in civilian aviation. And that's why self-analysis can provide some help in providing some level of assurance for this type of flight software. And so we get formal verification because we use sound self-analysis, and it's also cost effective because we just analyze the code and we don't need to some kind of re-engineering or implementation of the code. And we have run the IKOS on a number of autopilots or platforms like Paparazzi, Arduplane, and a flight control, NASA developed flight controller. And we managed to get a very low level of false alarm. In that case, it was for verifying the absence of buffer overflow, and with very low analysis time. And all these experiments were done using the buffer overflow analyzer that was less than 1,000 lines of C++. So we could rapidly develop a static analyzer that would yield very precise results on real code. And we are currently developing a specialized static analyzer using IKOS to address Autocode produced from MATLAB Simulink model. Because MATLAB Simulink is increasingly used to develop navigation software, especially at NASA. And the idea would be to have a static analyzer that can automatically prove a number of critical properties of the code with a very high level of precision, and to have it tailored for that particular type of article. And there is also some ongoing efforts to transfer the technology to NASA missions, and we are working with the GOSA mission team. GOSA is an Earth observation satellite, the new generation of Earth observation satellites, commissioned by NOAA. And we are partnering with group that works on the ground segment, and we are trying to apply the IKOS technology to the science code, which is a mission critical part of the software. And so that's interesting because we are really trying to apply the technology to a new class of application science code, and we are testing really the limits of the technology. So, and that looks quite promising. Okay. So, conclude. Static analysis can be a really effective tool for for providing formal verification of critical properties of software, especially flight critical software. And that's no miracle. We need to specialize the stack analyzer in order to get good performance and a low rate of false alarm. And we believe that our experiment with IKOS is a good step toward streamlining this effort and this design of a specialized analyzer. So maybe it's one step toward productizing or really making customized static analyzers usable and practical in real operational. And if you have any questions.
Please press star then one if you do have a question. 1 moment, please.
All right, we've got about 2 minutes for questions. Are there any questions in the room? No questions in the room. Any questions on the phone?
No questions.
Okay, I don't have any questions online yet, but if I get them, I will send them to the breakout room. Okay, Arnaud?
Okay.
All right, and we'll see you over there.
Okay, thank you.
Thank you. I'm going to go ahead and